Now that you know a bit about both rate of reaction and equilibrium, it's important to be able to bring those two things together in order to discuss the conditions used for industrial processes. Because both of those things tend to be important. A lot of industrial reactions are reversible reactions, and so having a favourable position of equilibrium in order to maximise the yield of the product you want is important. But also, of course, it's got to be produced at a reasonable rate. There's no point getting a fantastic yield if it takes you decades to get there. You need to be able to produce it in a reasonable time if you're doing it as an industrial process. So you have to be able to bring in both ideas. So let's use the classic example of this, which is the Haber process. So we've got nitrogen reacting with hydrogen to give you ammonia. So that's the reaction we're going to think about, and delta H for that is about minus 70 kilojoules per mole. Remember, that means minus 70 in the forward direction, plus 70 going backwards. So what we need to do is to think about what are going to be the best conditions. How would you choose the best conditions in terms of temperature and pressure and so on for producing ammonia? So the idea is that we want as high a yield of ammonia as possible, produced at as high a rate as possible, because that's what's going to make for a good industrial process. So let's have a think about what that means in terms of temperature and pressure. So we can think about increasing the temperature, or we could think about decreasing temperature. It doesn't matter, but let's just say let's think about increasing the temperature. Well, what will it do? Well, in terms of the equilibrium, you can see that it will shift the equilibrium in the endothermic direction. Remember, that's what Le Chatelier says. And always use the Le Chatelier language. So shift the equilibrium in the endothermic direction to oppose the change. So we're taking heat away in order to oppose the temperature increase. Which is the endothermic direction? Remember, this sign tells you that that minus sign tells you that the forward reaction has the negative delta H, so the forward reaction is exothermic, the backward reaction is endothermic. So it's going to shift in the backward direction in order to oppose the change. So you have to spell that out. Shift in the backward direction. Thus decreasing the yield of ammonia. Okay, so high temperature is bad news in terms of equilibrium, because the higher the temperature, the more the equilibrium lies over this way, so the less ammonia you'll get. On the other hand, what increasing the temperature will also do is increase the rate at which ammonia is produced. Because, as you know from all the stuff you've done on rates of reaction, that higher temperature increases the frequency of successful collisions. So you can see that they're in conflict. Equilibrium considerations are saying go low in temperature, but kinetic considerations, things to do with rate, are telling you go high. So in practice, what that means is that a compromise, that's the key word, Okay, a compromise temperature is needed. And you can spell that out, that it's high enough for a reasonable rate, without decreasing the yield of ammonia too much. Okay, so that's a really important idea, that you can't just say, oh yeah, high temperature is good or low temperature is good, because they have sort of opposing effects on these two aspects of what makes a good process. So introducing the idea of compromise when you're talking about industrial conditions is really important. What you could also bring in at this point is the catalyst, because a catalyst allows a lower temperature to be used. Okay, because if you're going to speed up the reaction by putting a catalyst in there, you won't need to go to as high a temperature to get a reasonable rate. Okay, allows a lower temperature to be used while still getting a good rate. So a higher yield can be obtained. So the catalyst, you can see, is a win-win thing here. It's not just that, oh, lower temperature is good because there's less fuel costs and stuff, but a lower temperature actually increases the equilibrium yield of ammonia. So the catalyst is a really good thing here. So a high yield can be obtained. Okay, so when you get questions like this about industrial processes, you've got to make sure you go through it in enough detail. Don't just focus on the equilibrium or just on the rate. Focus on both and explain what the compromise is. So that's temperature. What about pressure? Well, again, we have to think about both things, the position of equilibrium and the rate of reaction, when we're thinking about the effect of increasing or decreasing the pressure. So let's do those then. So increasing the pressure. First of all, what does Le Chatelier have to say about that? Well, you can see if we add... Oh, I'm absolutely got a balancing number missing there. You can see that on the left-hand side, we've got 4 moles of gas, but on the right-hand side, we have only 2. So increasing the pressure is going to shift the reaction in the forward direction, because it's going to cause the equilibrium to shift in the direction where there are fewer moles of gas, because that will oppose the pressure increase, and that means it will shift in the forward direction. So that's good. That's going to increase our yield of ammonia. So it will shift the equilibrium in the forward direction, because this decreases the moles of gas, is what the equation tells us. 4 moles goes down to 2, so opposing the change. Okay, so that's the Le Chatelier language of opposing the change coming in there. So that's looking like high pressure is going to be a good thing for getting a good yield of ammonia. But what about the effect on the rate? Well, increasing the pressure is the same as increasing the concentration. It has the effect of pushing the particles closer together, and therefore if they're closer together they'll collide more often, and so the rate will be higher. So actually that's good as well. Increasing the pressure will increase the rate because the molecules are closer together and so collide more often. So you might think, okay, let's go for as high a pressure as we possibly can, because that's going to give us a fantastic yield and an incredibly high rate. But of course it's not as simple as that in the real world, because high pressure comes at a cost. To some extent, in terms of running costs, that obviously it requires fuels to power the machines that will compress the gases. But actually the biggest cost is constructing the plant. Because to work at high pressures, you have to have really, strong walls and things. So the equipment has to be built to a very different specification, with a lot more materials involved and a lot higher stringency in terms of its ability to withstand things. So that the capital cost of setting up the plant is huge. And of course there's also a safety issue, that the higher in pressure you go, the more dangerous it becomes if something goes wrong. The risk of an explosion becomes much greater if the higher the pressures there are. And so there is a practical limit as to what you can do. So the compromise is, in this case, is not between yield and equilibrium, because those are both saying go for high pressure, but the compromise is that pressure can't be too high, as this would be too dangerous and too expensive. So again, there's always a compromise somewhere. There has to be a reason why a particular pressure is chosen, a particular temperature is chosen, and you have to express that choice in terms of it being some sort of compromise. Okay, so you can see that you can get quite long discussion questions based around choosing industrial conditions, and the risk is that you only talk about some of the story. So what you've got to constantly remind yourself is think about both the pressure and the temperature and the role of the catalyst, and think about both yield and rate of reaction. And if you bring all those things in, you get the complete picture.